Hello, welcome to this video. In this video, we will learn about vapor compression refrigeration system. Now, before we start talking about exactly how vapor compression refrigeration system or VCRS works, let us answer or try to answer few of the questions. You might have seen during summer, the easiest way to keep the water cold is to keep them in clay pots. I mean, from zeroth law of thermodynamics, you may always argue that the temperature in the clay pot should also be of the same temperature of the surroundings. But you can feel the difference that the temperature of this water in the clay pot is cooler than the normal water, correct? Now, the second question is, why do we feel cool when sweat evaporates from our skin? Remember, whenever we work out or when temperature is higher, we sweat, and it is the way by which body tries to keep our temperature normal. All right. So, when sweat evaporates, yes, we do feel little cool. And let us take one more example. When you apply perfume or sanitizer on our skin, so we also feel cold. So, what is happening here is of importance from the perspective of defining how a vapor compression refrigeration system works. Let us start with the first example. Yeah, if you are talking about a clay pot, it is very important to understand that a clay pot, a clay pot which is porous in nature. I mean, water, if you touch the surface of this pot, you can sense that there is water layer on the surface. Now, that means water from inside is reaching to the outside surface. From there, it goes on to evaporate. So, that is what is very important in cooling of this water. Now, if this evaporates, during evaporation, it takes away latent heat. That means the amount of heat which it requires for converting from liquid to vapor. So, latent heat of vaporization is absorbed from this water. All right. That is why you can see that the temperature here is lesser than the surroundings, because continuous evaporation will be there, and evaporation needs the energy which is taken from this water inside. So, you will get water which is relatively cooler than the surrounding temperature, and it is also true with the second example. So, when do we feel cooler? When sweat evaporates. I mean, during summer or whenever the temperature is higher, or even if your body is active or you are working out, then body sweats. Now, body sweats, but only when it evaporates, you feel little comfortable. So, there also the process of evaporation is there or vaporization is there. So, during which this latent heat is absorbed from our body, so we get cooler. And similarly, when you apply perfume or sanitizer, you can see that the moment, because they are stored at higher pressure, the moment you apply them, they start evaporating. So, here also evaporation is the one which is making us the sense of cold, right. Now, if you have a liquid which can readily evaporate, we can get the cooling. All right. The idea is pretty simple now. If we have a liquid which can evaporate readily at room temperature and pressure, we can always give cooling. Now, let us take an example of ammonia. Now, ammonia's boiling temperature is minus 33.3 degrees Celsius. Obviously, at room temperature, this will be vapor, because ammonia would have boiled at minus 33.3 degrees Celsius itself. The moment it is minus 32 degrees Celsius only, it would have become completely vapor. So, the moment you are talking about room temperature, this ammonia will no longer be in liquid state. So, if at all you want to keep this ammonia in liquid state, you have two options. One is ammonia should be lesser than minus 33.3 degrees Celsius. That means, if you go to say minus 34 degrees Celsius, it will be liquid. If you go to minus 32 degrees Celsius, it will be vapor. Now, this is where the phase change is happening. Now, the idea is clear. If you want the ammonia to be in liquid state, either you will have to cool it to liquid state, you will have to cool it to minus 34, or the moment it is greater than that minus 33.3, it will be in vapor state. Now, there is another option. The another option is you can pressurize to increase the boiling temperature. Now, if you increase the pressure, this boiling temperature of ammonia keeps on increasing, alright. So, it may be like this. So, there is a point where the pressure is so high that this comes down to room temperature, let us say plus 30 degrees Celsius. So, you can make it liquid by this technique also. You can pressurize to such an extent that the boiling temperature goes to room temperature. So, that is how you can make it liquid. Now, the idea is, if you give me the ammonia in liquid state, I can readily give you the cooling. Give me the ammonia in liquid state, the moment the ammonia is here at room temperature, it readily evaporates. So, what I will have is, if you give me ammonia in liquid state, I will keep it in a tank where I will keep the vegetables or fruits here, and as this passes here, this keeps evaporating. So, that means you can take out the ammonia in vapor state here, and obviously the heat is removed from here, because during this phase change there is latent heat of evaporation absorbed from this place. So, that gives me the cooling. But how do we produce ammonia in liquid state if you have enormous amount of supply of ammonia? So, you can keep on doing this, but you do not have such supply where you will have to, the idea is you will have to bring back this ammonia vapor and make it liquid state. Now, how do we make this? If I give you ammonia in liquid state, it is, you can give the cooling because its boiling temperature is minus 33.3 degrees Celsius. So, straight away we can get the cooling of minus 33.3 degrees Celsius. But if we have enormous amount of supply of ammonia in liquid state, how do we get ammonia in liquid state? It will no longer be available in liquid state, because the temperature itself, boiling temperature is minus 33.3. The moment you are minus 32, it is in vapor state. So, obviously, at room temperature, you do not find ammonia in liquid state. So, the idea is, if you can pressurize to make it liquid, then again you can use it. So, the idea is, if you are taking the ammonia from here vapor, bring back and make it to liquid. So, this is the process which we want. Ammonia should be liquefied. Again, how do we do it? Pressurize is the technique, because if you increase the pressure, the boiling temperature increases, there will be a point where it becomes liquid at room temperature only. So, the idea of using vapor compression is to use the refrigerant such a way that you are going through, the refrigerant will be going through liquid, vapor, and again in the same cycle. So, now let us talk about the refrigerants which are generally used. So, these are the refrigerants like R12, you have boiling point minus 29.8, R22, R134A, which is quite famously used, R717, carbon dioxide, ammonia, isobutane, propane. Okay. Now, let us talk about the block diagram of vapor compression refrigeration cycle. A typical vapor compression refrigeration system will have an evaporator, and a compressor, and then a condenser, and then a pressure reducing valve, which is often known as throttling valve. Okay. Now, a compressor as we said, it is a vapor compression. Compressor can handle vapor. So, at point 1, you would expect the refrigerant to be vapor, all right. So, but the pressure will be low. So, we will talk about that. Pressure will be low. Low pressure vapor will be the state of the refrigerant here at state 1. Now, at state 2, we will have pressure increased by the compressor, but the refrigerant will be still in vapor state. So, high pressure vapor will be the state. And then after condensation, we expect it to be 0.3, we expect it to be liquid, but high pressure. Okay. Now, after throttling valve, we will get here partial vaporized, partially vaporization is happening. So, refrigerant pressure is dropping. So, pressure dropped. All right. Now, this will be 0.4. Now, let us talk about this again. So, what was the idea with which we started this? We wanted a refrigerant to evaporate. During evaporation, so that means you want the liquid here, and the moment it evaporates here, so you have vapor here. So, how do we make it evaporate? By dropping the pressure. So, if you have a liquid, it readily gets converted into vapor, the pressure is dropped. Now, vapor has to be brought back to liquid state again. Now, how do we bring it back to liquid state? By pressurizing it, as we have discussed. If you increase the pressure, you can bring down the vapor to liquid state. But here with the pressure, temperature has also increased. So, at point 2, it is still in the vapor state. If you bring down the temperature a little bit at point 3, it becomes liquid, and again the cycle continues. You drop the pressure in a throttling valve. So, throttling valve is a isenthalpic device where enthalpy remains same whereas pressure is dropped. So, the idea is you have a liquid, convert it into vapor, you bring it back into liquid state again by raising the pressure. So, this itself is what we call it as vapor compression refrigeration system. Now, let us talk about the PV diagram, pH diagram for the same, or TS diagram for the same. Now, if we start with PV, pH and let us say TS diagram. PV diagram. So, we will have to have a vapor dome. Vapor dome is obviously will be there because there is a phase change of the refrigerant. Okay. Now, let us start with PV diagram. So, always what is the point 1? Point 1 is entry to the compressor. Entry to the compressor must be at least saturated vapor. We know that this right side line is saturated vapor, this line is saturated vapor. So, this side is saturated liquid. Okay. Now, at least it has to be here. I will start from here. Let us say this is our point 1. Now, how are we compressing from 1 to 2? 1 to 2 is reversible adiabatic compression or isentropic compression. So, in a PV diagram, we know the process looks like this. So, I will take it from somewhere here, that is point 1. The process 1 to 2 reversible adiabatic compression looks like this. Okay. Now, 2 to 3 is a heat rejection in a condenser. So, heat is rejected in condenser, heat is rejected in condenser. So, it is a constant pressure process, it is assumed to be constant pressure. So, constant pressure process in a PV diagram looks like a horizontal line, and it is expected that After cooling, it has to be saturated liquid. So, this is 0.3. So, I am going for saturated liquid line. Again 3 to 4 is throttling process, but enthalpy remains constant, isenthalpic process. So, it is isenthalpic process, enthalpy remains constant. Now, this is 4, this is 4, and 4 to 1 is constant pressure heat absorption. I mean, from perspective of refrigerant, it is absorbing the heat. So, it is Q, let us say absorbed, or heat removed from the refrigerator, we can call it as. So, it is again constant pressure. So, constant pressure looks like this. This is entropy constant, RPV per gamma is equal to constant. Now, we can see, let us go for pH diagram. Now, in pH diagram, we must understand that the process is happening between two constant pressures, alright. So, that means you can readily draw two constant pressure lines first, and then we can start working, okay. Now, let us start from this point, let us start from dry saturated point, that is here. So, this is our 1, this is our point 1, okay. Then process 1 to 2 is isentropic compression. So, 1 to 2 looks like this, that is S is equal to constant look like this in a pH plot. So, this is entropy constant line, this is entropy constant line. So, 1 to 2 is reversible adiabatic compression. Now, what is 2 to 3? Heat is ejected such that it becomes saturated liquid. So, we must go from here to at least till here. So, that is 0.3, 0.3 is here. Then 0.3 to 4 is again isenthalpic process, and enthalpy constant in a pH plot is a vertical line. This is enthalpy constant, this is pressure constant. So, this is 4, and 4 to 1 is a constant pressure process, and within vapor dome you end up with a horizontal line. Okay. So, this is our pH plot. Now, let us go to TS plot, temperature versus entropy. Now, what is 1 to 2? 1 to 2 is isentropic compression, we are talking in terms of entropy plot. So, it will be vertical here. Okay. Now, this is our 1 to 2, and then 2 to 3 is constant pressure. Outside the vapor dome, constant pressure will be looking like this. Okay. So, then you will have constant pressure within vapor dome like a horizontal line. So, this will be our 2 to 3, and again 3 to 4 is isenthalpic process. In a TS plot, enthalpy constant would look like this. So, this is our enthalpy constant, this is pressure constant here, this is entropy constant here. So, now at last you have 4 to 1, which is a constant pressure line. So, this will be our 4 to 1. Okay. Now, we can derive the efficiency equation or COP equation. Let us concentrate on pH diagram only now. Now, remember 1 to 2 is compression, 2 to 3 is heat rejection, 3 to 4 is throttling, and 4 to 1 is heat removed. So, this is what is desired actually, heat removed from the controlled space. Okay. Now, COP is what? COP is desired output by input. Now, what is desired in a refrigerator? Heat to be removed. What is the input we are giving? Work. Now, what is heat removed here? Heat removed here is, I mean, we can reduce this equation, will come down to enthalpy difference only. From first law for a steady flow energy equation, you will end up with Q is simply enthalpy difference. So, QL will be simply H1 minus H4, highest minus lowest we are taking. highest will be H1 because H is varying in this direction, highest will be H1, lowest will be H4. Similarly, where is the work? Work is happening between 1 and 2, that is compression. You are supplying electrical energy from 1 to 2. So, that will be H2 minus H1. So, that is it. That is the formula which gives us the COP. All right. So, we can start solving numericals on this in the next class. Thank you.